Hello. PV loops are the gold standard for measuring direct, real-time cardiac function, but the technology, and more specifically the calibration procedures, can present a challenge to new researchers to the technique. In this video, we'll explore common calibration shortcuts, and take a look at how avoiding calibration by using estimates produces inaccurate results in both admittance and conductance PV systems. So why doesn't everyone just calibrate? The reason is that calibrating a PV catheter can be technically challenging, time-consuming, and potentially expensive. These pressures drive researchers to use estimates, or default values for calibration parameters, instead of calibrating the system for individual animals. For users of admittance technology, this has now become the recommended approach to arriving at volume-calibrated data. But estimates often assume that every animal in the study is identical. Using estimated calibration values will ultimately impact how accurately you can report on certain volume-derived measures of cardiac function, like stroke volume, which may be important to your research question. Fundamentally, both admittance and conductance systems require a series of calibration steps for accurate measures of volume. These steps are designed to overcome two main sources of error. Firstly, the surrounding heart tissue conducts electricity and contributes to the overall volume signal. This component must be removed. And secondly, the electrical field produced by the catheter is not uniform. To account for this, a field correction factor, calculated from an independent measure of stroke volume, is used as a final adjustment to the volume signal. Let's look at how failing to do this final calibration step affects a commonly reported cardiac measure, stroke volume. We recorded PV data for both admittance and conductance systems from the same 5 healthy rats and analyze the resulting data. First, let's look at what happens with the admittance system when estimated values are used instead of calibrating. Admittance users often use the stroke volume estimations that are provided with the admittance system. These estimates are based on the health, or in some cases the weight of the animal. In this example, we compared these suggested estimations to an ideally calibrated admittance system using Echo. Let's look at the PV loop data from just one rat. Here, the volume signal is calibrated using the default 200 microliter stroke volume estimate for a healthy rat. When we compare this to the ideal calibration using Echo, here, we can clearly see there's a large difference in stroke volume for that same rat. When we use the other suggested estimate, based on the weight of the animal, here, we get an even greater difference in the stroke volume. When we look at this across a group of 5 animals, the use of the default value estimate consistently results in an overestimation of stroke volume in comparison to the Echo calibration. In addition, biological variability of the stroke volume values is reduced when using this estimate, causing all of the reported values to be tightly clustered around the reference value of 200. Essentially, by selecting the same stroke volume reference across a group of animals, you're predetermining your output stroke volume data. Also concerning, if we look at the impact of using an estimation by weight, we get an even greater overestimation of reported stroke volume, on average 134 microliters, when compared to the fully calibrated system. As we can clearly see, choosing to use an estimation over properly calibrating your system, as many admittance users are encouraged to do, will give you a set of results that may no longer be physiologically relevant. Now, let's look at what happens when the calibration step is missed for the conductance system. With the conductance system, researchers commonly avoid calibrating the field correction factor, known as alpha, by eliminating the variable entirely and assuming the scaling factor to be 1, or less commonly, by using an average value calculated from a group of similar animals. Looking at the data from a single animal, assuming the alpha scaling factor to be 1 will most likely give you an underestimation of volume compared to a fully calibrated system using Echo. Using the average alpha value results in an overestimation of volume for this animal, but the results are variable between animals. Now if we look at the impact of these two decisions across our same group of 5 animals, you can see that compared to a fully calibrated system using Echo, here, eliminating the calibration factor results in an underestimation of stroke volume, on average 39 microliters across the 5 animals. And again, in the instance of using an average value, the resulting stroke volumes are different from the results of a fully calibrated system, but generally remain in a similar measurement range. As we can see, omitting just one of the calibration steps can impact the data you are reporting on in both admittance and conductance systems. Choosing to use estimated values across a group of animals will impact your ability to accurately report on volume-derived measures of cardiac function, like stroke volume, which may be important to your research question. As such, we strongly recommend you consider the effects that not calibrating your system properly will have on the accuracy and credibility of your results. Thanks for watching. For more in-depth analysis, including the effect of using estimated values for parallel conductance calibration, please follow the link on screen.